Hello and welcome back to another video on our course Competition, Policy and Strategy. In this video and in the subsequent videos we will talk about the solutions to assignment number 2 covering the topic oligopoly. More specifically, in this video we will go through the solutions of the first assignment of the first exercise of this second assignment called exercise 2.1 Nash equilibrium. Now in this exercise we are faced with a situation which I will sketch briefly just so we don't have to go through all of the details that are laid out, like the whole story laid out on this slide. So in this situation that we are about to analyze, we assume that there is two profit maximizing firms, two profit maximizing airlines to be more specific. Let's call them airline A and airline D. These two firms decide simultaneously on the departure time of their respective flights from London to New York. We will assume that the price is fixed of these flights and that these firms have only one strategic variable to choose. And this strategic variable is whether they want to depart in the morning or to depart in the evening. These are the only two options of the firms by assumptions. Depending on the departure time, different numbers of passengers will buy the tickets to the flight, right? And we will assume that in turn a higher number of passengers yields a higher payoff, all right? And now all this setup can be summarized in one very simple table which you see in the lower part of the slide, where we now have the two airlines, the D airline and the A airline. And for each airline, we see the strategies they can choose from in the rows and columns respectively. And then what we see in the single cells, so in the combination of the row and the columns, is the payoffs of each firm. And just so we're all on the same page when it comes to reading these kind of tables, the first number in these brackets, the first number tells us the payoff of the first firm. And the first firm is always the one that is written in the rows. The second number in each of these cells tells us the respective payoff of the second firm. And the second firm is always written in the columns. All right? But before we get into analyzing these games, we will have to talk about the specific terms, the vocabulary that we will use when analyzing these kind of games. So, the first thing that we are asked to do is to specify what is meant by the terms players, actions, payoffs, and information in the context of game theory, because as you may have noticed, that's the context we are now entering. We are furthermore asked to specify what players, actions, payoffs and information are in the previously described game. So first let's talk about what's that in general, and then second let's point out what this respective term captures in the game we are analyzing. Let's start with players. Players are usually denoted are understood as a set of n players. And what we mean by players is the agents that are active in the game and pursuing their self-interest based on the rules of the game. Simple as that, right? So what are the players in this game that we are faced in this exercise? Well, the players that are pursuing their self-interest based on the rules of this game are, in our example, the airlines A and D. The second term we need to talk about is actions. Actions are understood as a set of strategies, and this set of strategies will be called sigma I. I is indicating that we are talking about player I, all right? So actions are understood as the set of strategies sigma I, which contains all possible actions of a player I. strategy space then captures all strategy profiles of the individual players. So when we denote the strategy space, sigma, without any index, it's simply the cross product of all the individual strategies, sigma I, of each individual player. Now finally, this strategy space contains all strategy profiles, which we will denote with a lowercase sigma, again 1 to n, of all players. In this specific example that we are talking about, the set of strategies, the set of strategies of player A and player D are equal because both airlines have to their availability the strategies of flying in the morning or flying in the evening. So the strategy space for both players equals the set of morning and evening. Next is payoffs. Payoffs are understood as a function of the player's own strategy and the strategy chosen by all other players. All right? So the result of the game based on the strategies each individual player chooses, right? In this specific example, in this specific game we are about to analyze, one example for a payoff would be 150 in case both players are choosing morning, right? So in case both players choose the strategy morning, then the payoff of both players will be 150 in our example. Fourth and finally, let's talk about the term information. In general and throughout this course, we will distinguish between incomplete information and complete information. Let's start with maybe the more simpler term. Let's start with complete information. In case we are talking or we are assuming that players have complete information, what we mean is that there is no uncertainty. No uncertainty in particular with regard to the payoffs and the strategies of all players. In contrast to this, when we are talking about the case of incomplete information, well then the contrary is true. So that there is uncertainty regarding the payoffs or the strategies or both due to, for example, simultaneous turns. So players simply cannot see what the strategy of the opponents or the other players are until they are moved themselves. Or, for example, a move by nature. And what we mean by a move by nature is simply randomness in a very generally speaking. Or a move by chance. In this specific case that we are talking about, well, let's think about the setting that we sketched earlier. All players, so both players, know that the available strategies are either flying in the morning or in the evening, and all players know by assumption the payoffs because they know the expected number of passengers, right? So in our case, we are talking about complete information. Now that these terms are defined and understood, let's talk about the Nash equilibrium. We are asked to explain what the Nash equilibrium is, and then we are asked to find all Nash equilibria in pure strategies in the game that we have described before. So what is a Nash equilibrium? A Nash equilibrium is a strategy profile, and strategy profiles, as defined earlier, are denoted with a lowercase sigma, and because it's an equilibrium, we stick to our convention of marking equilibria with an asterisk. So the strategy profile sigma star, which of course contains one strategy for each player, is a Nash equilibrium if the chosen strategy of each player is the best response to the best responses of all other players. Now, of course, in order to understand what this means, we need to understand what is meant by a best response, right? And this will become more clear once we analyze the exemplary game that we are going to talk about in this exercise. But generally speaking, best response means that considering the strategy of all other players, player I is choosing their own payoff maximizing strategy, right? And then a best response to the best response, this recursion means that all players are choosing the payoff maximizing strategy, considering that all other players are choosing their own payoff maximizing strategy. And by this, it's quite intuitive, I think, that we will end up in an equilibrium. Because if everybody is choosing their payoff maximizing strategy, then no player has a reason to deviate. All right? All right, now that we know the general definition of a Nash equilibrium, let's try to find the Nash equilibrium in the very exercise, in the very example that is given to us in this exercise. And one way of finding the best response of all players regarding the best responses of all other players is to go through each best response and underline it in the matrix. We will do so step by step in the following. So let's start by considering, or let's start by finding out what are the best responses of the D airline considering the actions of A airline. How do we find out what the best responses of the D airline are considering all possible strategies of the A airline? Well, one way to find out is by simply going through each single strategy of the A airline and considering each single time what the best answer of the D airline is in the specific case at hand. So let's do this one by one. In the first step, let's assume for a moment that the A airline is playing their strategy morning. And the question is, what is the best response of the D airline considering A airline is playing morning? So what we are now comparing is the payoffs of the D airline, which, as we discussed earlier, is always written as the first number in the tuple. We are now comparing the payoffs of the D airline for each possible response on the strategy morning played by the A airline. All right. So the D airline has two choices, has two options. It can either fly in the morning or in the evening. And given that A airline is flying in the morning, we see that the D airline is receiving a payoff of 150 in case it chooses to fly in the morning at 2, and it receives a payoff of 500 in case it chooses to fly in the evening instead. It's hopefully quite obvious to see that 500 is larger than 150. So the best answer of the D airline on the strategy morning played by A airline is to choose evening, right? So let's underline evening. Now let's find out what is the best response of the D airline in case A airline is not playing morning but instead is playing evening. All right, so we are now looking at the second column of this table. And again, if we want to compare the payoffs that the D airline receives in case A airline is playing the strategy evening, we again have to compare the numbers written first in the tuple. All right. So now the D airline, now we can see that the D airline will receive a payoff of 300 in case it chooses to play morning, and that the D airline will receive a payoff of 400 in case it chooses to play evening too. Again, by comparison, 400 obviously is larger than 300, so we know the best response of the D airline towards the strategy evening played by the A airline is to play evening as well. All right? So, again, let's underline evening. We now know the best answers of the D airline on any strategy of the A airline, right? So we are basically done with finding out what the best responses of the D airline are. But in order to find the Nash equilibrium, we of course need to know the best answers of all players regarding the strategies of all other players. All right? So let's do the exact same thing that we just did for the D airline, but now from the perspective of the A airline. So again, let's start by assuming that the D airline is playing the strategy morning, and let's find out what the A airline's best response is towards this strategy. So we are now looking at the payoffs written in the upper row of this matrix. And we are comparing, because A airline is the second player or the player written in the columns, we are now comparing the second value of each tuple. And similar to what we just saw for the other airline, we see that playing the strategy evening yields in a higher payoff, namely 500, than playing the strategy morning, which yields in a payoff of 150, assuming a given strategy of morning played by D. All right, so let's again underline the best answer of the A airline towards this specific strategy of the D airline, which is evening. Now, finally, fourth and finally, let's find out what the best response of the A airline is, assuming or considering rather that the D airline is now playing the other strategy, namely evening. We are again comparing payoffs the payoffs that are written second in the tuples, and we are now considering the lower row of the matrix. We are comparing 300 in case A airline chooses to respond with playing morning with 400 in case airline A chooses to respond with evening. Obviously 400 is larger than 300, so the best response of airline A towards this strategy of airline D is to play evening. We have now found out all the best answers of all players towards all possible strategies of the other player. Now, which of these cells contains the best answer to the best answer? There is only one single cell in which we have underlined both values, right? And what this means is the best answer of the D airline playing evening is for the A airline to play evening as well. And the best answer of the A airline towards the strategy of playing evening by the D airline is to play evening as well, right? So in this cell we have the case, it is the case that both players, or in this case all players, are playing the best answer to the strategy of their opponents, which is the best answer to their own strategy. So only in this single cell all players are choosing their best response to the best responses of all other players. Hence, this cell contains the Nash equilibrium. All right. Now we are going to do this procedure a few more times, just to reiterate and just to to recapitulate what we just learned and yeah, to get a better understanding. So we are now asked that to find, for all the 4 games that are coming in the following, to find all Nash equilibria in pure strategies. And then as an optional task, each of these games has a conventional name, simply because of these patterns of payoff that we will see in the following are very common, and therefore at some point they earned their own name. Alright, let's start with the first game, game A. And in order to find the Nash equilibrium, we can do exactly the same that we just did previously. Let me just do this once more in this video, and for the next 3 games I will simply present you the solutions, just because I don't want to reiterate too much and to repeat myself all over. So in this game we have player 1 and player 2. Player 1's strategies are written in the rows. Player 2's strategies are written in the columns. Now let's find the Nash equilibrium, or in other words, let's find the best answer towards the best answers. Let's find the best response of all players towards the best responses of all other players. Let's first consider a situation where player 1 is choosing to play the strategy up, so the upper strategy. What is the best response of player 2? Now we have to compare a payoff of 1 with a payoff of 2, so obviously given player 1 chooses to play the upper row or the upper strategy, the best response of player 2 is to choose the right strategy. Okay? Let's now consider the second strategy for player 1. Let's now assume player 1 chooses down, so the lower row. Then player 2 can compare, or has to compare, the payoff of choosing L, which is -1, or choosing R, which is 0. Obviously 0 is larger than -1, so the best response of player 2 again is to play right. Now we already know, at this point we already know all the best responses of player 2. Let's do the same for player 1. So let's assume first the case where player 2 chooses to play the left strategy. Player 1 now needs to compare a payoff of 1 in case they are choosing up with a payoff of 2 in case they choose down. Obviously 2 is larger than 1, so the best answer, the best response of player 1 is to choose down. Finally, let's consider the situation where player 2 chooses the strategy right. Now player 1 compares a payoff of -1 in case they are choosing up and a payoff of 0 in case they are choosing down. Obviously 0 is larger than -1, so the best response of player 1 towards a strategy R of player 2 is to play down. We now see the exact same pattern that we just saw in the previous example, which is that only in the bottom right cell we see that both players are actually playing the best response towards the best response of the other player. Alright? So we again have one single Nash equilibrium, in this case defined by the strategies D and R. Alright? Now the name of this game is called Prisoner's Dilemma. Why is it called Prisoner's Dilemma? Well, the easiest way, of course, would for you to read on the Prisoner's Dilemma, because I'm sure there is a lot of explanations out there that are way better than mine, but a very easy way to remember why this is called the Prisoner's Dilemma is, well, just have a look at the patterns of the payoffs. What you will notice is that actually in this up left corner, both players have a higher payoff, namely 1 and 1, which is for both players more than the Nash equilibrium, which is 0 and 0 as payoffs. However, this Pareto superior payoff or result of the game can never be reached, because both players have always an incentive to deviate from this strategy and thereby increase their own payoff, right? So just for a second, consider a situation, just assume both players are considering playing up and L respectively, so we are actually in this upper left quadrant. In this situation, of course, player 1 can put themselves better off by switching strategies and not playing up, but instead playing down, and thereby increasing their payoff from 1 to 2. And the exact same argument holds for player 2. Just go through it. Yeah. You can make an analogy where this resembles a situation where you have two prisoners, and in case they are both lying and deny, like they are investigated by the police, they are asked by the police, and in case they are both denying the crime, nobody can be found guilty because there is no proof, and both will have a payoff of 1, like the largest payoff possible for themselves. But then the police goes ahead and offers a leniency program whereby they increase the payoff of the one person that is actually telling the truth and providing evidence that helps to punish the other criminal. So this game is called Prisoner's Dilemma because the individual deviation from sticking to the collusive behavior is always profitable for the individual, and therefore both players end up in this Pareto inferior situation, which at the same time is the only Nash equilibrium of this game. And they have, without communication and without binding contracts, etc., the players have no chance of reaching the actually, for both of them, better outcome in the upper left corner. All right. I'm spending quite a few minutes on this one game because it is one of the more frequently discussed games, and more importantly, this is the very concept that we will base future contents of this course on, namely the prisoner's dilemma, which we will need to rely on, or which we will need to come back to once we are talking about collusion and cartels and deviation from cartels as well. All right? So for the next games, I will keep up. I will pick up the pace a little bit. So in this game B, we can see by using the same method which I now illustrated twice in this exercise, that there is actually two Nash equilibria. One Nash equilibrium is in the up left, the other one is down right. This game is called Battle of the Sexes. There again is a lot of literature on these kind of games. Let me just broadly sketch the story behind this. So the idea is you have, of course, obviously two players. Let's assume for simplicity they are a couple. One of them prefers one activity, maybe going to the theater, and the other one prefers the other activity, maybe go to the cinema, and yeah, but they both have a preference for going anywhere together, right? So you will see that there's two Nash equilibria. Each one is preferred by one of the players, but again, meeting up, so to speak, is still better than choosing different options. All right. The third game, called the inspection game, basically because it's kind of the opposite of what we just saw. This game has no Nash equilibrium, right? Because there is not a single, you will notice that there is not a single pair of strategies that is the best answer on the best answer of all other players. So, name of the game comes from this storyline that these two players actually do not want to agree. Just consider somebody inspecting, somebody seeking. Scheiß drauf, schneide ich raus. Name of the game comes from players avoiding each other, and they have a preference for not ending up in the same pair of strategies. Game B again has two different Nash equilibria, one in the up right corner and one in the down left corner. This game is called the chicken game. And we call games with this general pattern of payoffs the chicken game.